Hello, we're going to talk about circles today and different parts of circles. And before we get into anything too interesting, let's just talk about a few definitions. First of all, we have something called a chord. And a chord is simply a line segment where both endpoints are on the circle. So you can see here this segment AB, both endpoints lie on the circle. So we call this segment AB a chord of this circle. Also, we have something called an arc. I think we know what an arc is for the most part, but it's part of the outside of a circle. Okay, so this darkened thing here is called an arc. And there are a couple things I want to make sure we know. First of all, we have two types of arcs. We have minor arcs and major arcs. Minor arcs are less than half of the entire circle. Major arcs are more than half. Notice that the points A and B create two different arcs. We have this minor arc AB, so we look at here, this is a minor arc because it's less than half a circle. But if I were to shade the other way, if I were to darken in this part over here on the outside, that would be a major arc. Okay, so for instance here, this is a different circle, but this CE is a major arc because it's more than halfway around. Last, I want to make sure we understand we can measure arcs by talking about arc length or its angle measure. If you ever hear just measure of an angle, or excuse me, measure of an arc, if you say what is the measure of an arc, that is always its angle measure. Okay? We only talk about length if you hear the word length, if it says length of arc, whatever. Okay? So the bulk of what I want to talk about today is what the relationships are between arcs and different angles within a circle. This is just definition we've already heard. I want to define something called a central angle. A central angle is an angle where the vertex is the center of a circle. Okay, so in this case we're talking about this angle right here, ACD. Right, this angle right there. And I'm going to change that to make it a little bit darker for you. So what we want to know is what is the relationship between this arc AD and angle ACD. Okay, and so if I show you, in this case, here's the length of our arc, or excuse me, the measure of our arc, and the measure of the angle, the central angle, is the same. Okay, so the big thing we need to learn here is that the central angle is always congruent or equal in measure to the arc that it creates. Okay, so let me pop that up here on the screen for you. A central angle always has the same measure as its intercepted arc. And intercepted arc, guys, that may be a new term, but it's intercepted just means the arc that's created by the angle. So in this case, arc AD is the same as angle ACD no matter what, no matter how we slice it, right? No matter how big this arc is or how big the angle is. That's fairly straightforward. Let's look at another situation. Okay, and what we're going to be investigating really is when I have two lines intersecting, obviously that forms an angle. We want to look at what happens when the two lines intersect in different places in relation to the circle. So obviously there's a couple things that can happen. One is two lines can intersect inside the circle, and you can see that there are several arcs created around the outside of the circle when that happens. Another thing is they could intersect exactly on the circle. In this case, there's one arc in between the two. Okay? We also have situations where they can intersect outside the circle. And so we're going to investigate how these things are related to each other in these different situations. So let's look inside the circle first. So here I have a situation. We have this arc GNI is this major arc we're looking at in this case, right here. Okay? I have arc KOJ. Okay, sometimes notice that we'll use three letters to define an arc just to make it more clear what we're talking about, right? Because if I just said KJ, we wouldn't know if that's the whole major arc or this minor arc. If, by the way, you're unsure and it only gives you two letters, that always means minor arc. But I put three letters in here just to make sure. Okay, we also have this angle KHJ and GHI that we are looking at. Notice that they're the same. I hope we know why that is. Think to yourself, the reason these are congruent is the vertical angle congruence there. But our question is, how are these two arcs that are intercepted by this angle, or these angles, related to these numbers? And it may be hard to see how this number is related to these two. And I can play around, but it probably is not going to help us see it. So let me show you. Okay, what this says here is that if I add this big arc GNI to this small arc KJ and divide by 2, in other words, if I take the average of them, I get this number right here, which if I look over here, you may notice they're always the same. It doesn't matter whether they're both minor arcs, whether one's a major and one's a minor. It doesn't matter what I do here. I hope you realize and are seeing what I'm seeing. This number is always the same as that number. And this is really great. Okay, this is a great thing to recognize. And we can generalize this and call this a rule. It's always true. It's always true. And what it says is that if two chords intersect inside a circle, then the measure of the angle formed by the two chords, so in this case it's these two angles, GHI and KHJ, is equal to the average of the two arcs measures on the outside. Okay, I hope you're noticing this, but you may be saying, well, what about this angle here and here? Well, the same thing would be true. If I measured this arc IK and this mark GJ and found their measures, I could take the average and it would be the same too. In fact, let me do that real quickly just to prove my point. Okay, so if I measure arc, here's arc IK, and then I measure arc JG, measure that angle, and if I take these, I'm going to keep going here, if I calculate and I do this plus this, and divide it by 2. I should have put that in parentheses. Sorry. So if I do this plus this, and I divide it by 2, we get 89.03. And lo and behold, if I measure this angle right here, you can guess it. It's 89.03. We can see that right here. Okay, so you know, I can move that around, and it's still true. So it doesn't matter which way you look at it. The intercepted arc's average is equal to that angle that's inside the circle. Okay, and I hope this makes sense to you, but I like to think of it this way because there's 3 different relationships we want to talk about, I mentioned. One's inside the circle, one's on the circle, and one is if they intersect outside the circle. And I want to kind of give you this visual. If it's inside, we just found out that it's the average of the 2 arcs that it creates if I were to continue these lines. And notice that the further I pull this point away, what should be happening here? It looks like this angle is getting smaller, even though this arc isn't changing. And that can give us some intuition into what to expect here. So if we have a situation where the angle is actually on the circle, okay, first of all, that's called an inscribed angle, so write that definition down. But in this case, maybe you can see a little more clearly what the relationship between these two numbers are. The arc is always bigger than the angle. And if you notice, it's exactly half as much. Okay, if I take the arc and just divide by 2, it gives me the same as this angle right here. Okay, and if you want to think of it in terms of the last thing, it's still almost like the average, but the second arc is 0. So if I add this to 0 and divide by 2, it's just the same as just dividing by 2. So we can make that a definition as well. And this is a fact that's always true. If I have an inscribed angle, meaning the vertex is on the circle, its measure is always exactly half of the whole circle's, or of the entire arc measure. And of course, that brings us to the last situation. What happens if they intersect outside? So remember, when it was inside, we added the 2 arcs and divided by 2. When it was on the circle, it was exactly divided by 2. So again, it's getting even further when I pull it back. And maybe you're kind of seeing a relationship here. I'm not going to add them and divide by 2, but this arc that's inside, right, and this arc that's inside, I'm going to take the difference, right? If I took the big arc and subtracted the small arc and divided by 2, notice it doesn't matter how big the arcs are, right? It doesn't matter how close this point is to the circle. This number right here, I'll move it, I'll move this over here so you can look at it, right? Though that angle, ABC, is always equal to the difference of the 2 arcs divided by 2. And we can write that down as well, right? So when the vertex is outside, then I take the difference of the intercepted arc. So again, this is what's inside the 2 lines, right? So there's one, I don't know why it's not showing it, but from A to C, right? This arc right here, okay? And I'll build the arc just so you can see it. Well, never mind. Screw all that. So I hope this makes sense. I'm going to work problems in class instead of right now, just for the sake of time. It's already right at 10 minutes. We're going to play with this some more, but the big key is inside, the angle measure is add the two arcs and divide by 2. If it's on the circle, I just divide by 2. If it's outside, I subtract the two arcs and divide by 2. And of course, if it's exactly in the center, it's equal to the same arc. So those are the relationships, and we will play with this tomorrow. Thanks.